So what we're going to do is basically summarise the lines of evidence that suggest that the Kekulé structure is an oversimplification. You actually still see it used a lot, and you can draw benzene like that, but you sort of have to do it with your fingers crossed and say, yeah, I know it's not really quite as simple as that. But actually in organic chemistry that's used a lot still to represent the benzene structure. But there is an alternative way of doing it, which is a shorthand way of showing that delocalized system with the two rings of electron density above and below the plane, and that is to draw it like that. So this is the structure showing the delocalization. And so we will tend to use that mainly in A-level stuff, but if you see that, it's not a mistake, because it's perfectly acceptable to still use that as a way of drawing the structure out. So let's look at what the lines of evidence are supporting delocalization. So we've already met the first one. So the first thing is low reactivity with electrophiles. Okay, we have to be able to explain why bromine fails to react with benzene in the dark. So there are sort of various ways of explaining this from a sort of chemical point of view, but the one that the exam board likes is based on the idea of electron density. So electron density means, if you like, how many electrons are there within a given volume of space. So if we think about cyclohexene again, which is that. Okay, so that's a localized pi bond, as opposed to delocalized, and it has two electrons focused along that one side of the ring. So if you like, two electrons along one side of the ring in the pi bond. Now if we think about the delocalized model, where we have this cloud of electron density, if you like, above and below the plane of the ring, if you think about it, each one of those p orbitals that overlapped to give you the pi system had one electron in it. So in total there are going to be 6 pi electrons in the delocalized system spread around the ring. Okay, so delocalized system has 6 pi electrons spread evenly around 6 sides of the ring. And you can see what we're coming round to is that where you've got 2 electrons focused in this region here, along each side of that ring, on average there's only going to be 1 electron. Okay, so there's only 1 electron on average, because remember, electrons don't have fixed positions, but we can say on average along each side. So that's a lower electron density. Now why does that matter? Well, to see how that works we need to remind ourselves about the mechanism by which bromine attacks an alkene group. So if we remind ourselves of the mechanism, so here's our alkene, and here's our bromine moving in to attack it. Remember, the key thing is that there has to be some kind of attractive force between the pi bond here and the bromine molecule. And it's not immediately obvious where that comes from, because neither of them is polar. But what we came up with was this idea that as the bromine approaches here, because the pi electrons are quite exposed, right, because they're not pinned down right in between the nuclei but exposed out to the side, they're sort of in your face as you approach here, and so they'll have quite a big repulsive effect on that electron pair here, and they will push it towards the back. So what happens is that you get a dipole like that. Okay, so that's a dipole induced by repulsion from the pi bonding electrons. And the reason that's important is that that now creates a hook which can grab those pi electrons out of the alkene molecule. So remember, that pair of electrons now gets grabbed by the delta positive bromine, and that causes that bond to break, and that gives you the key intermediate in the pathway, okay, which looks like this. So all the atoms are still there, but now that pi electron pair is instead coming down here to give you a bond to bromine. This carbon has been left short of an electron because it used to have a share in the double bond, in the pi bond, but that pair is now here, so that becomes positively charged. And this bromine has an extra electron because it used to be sharing this electron pair, but now it has them all to itself, so it becomes Br- with a new lone pair. So that's the intermediate, the carbocation. And remember, to complete the mechanism, that goes in like that. Okay, so Br- uses a lone pair to plug into this carbon that's short of an electron pair, and that completes the mechanism, so you get this addition reaction like this. So why does electron density matter? Well, it matters because right at the beginning you have to have this attractive force between the electrophile, which is the bromine, and the alkene. And that attractive force has to be strong enough to pull the electron pair out of its pi bond to form the new bond. And you can see that the problem's going to be that if you have lower electron density, then you're going to get less, first of all, less polarization of the bromine, right? Because if there's lower electron density here, it's not going to repel the electrons in this bond so strongly, so you're going to have a more weakly polarized bromine molecule. And secondly, the attractive force is going to depend on, you know, the size of the negative charge in the pi bond and the delta positive charge here. And of course, if there's lower electron density, then you've got, if you like, a smaller negative charge on this side as well as the positive charge on that side. So one way and another, having lower electron density makes it much harder for this reaction to happen, even if you have something that doesn't need polarizing. So if you have HBr, for example, like this, where your mechanism would now pan out very similarly, but you'd be adding hydrogen first and then bromine, so it works out like that. You don't have to have polarization this time because this molecule is already polar, but you're still going to get a weaker attractive force between the delta positive hydrogen and the negatively charged electrons in the pi electron system if they're delocalized, just because they're less focused in this point. So if you like, there are fewer of them in that part of the molecule. Okay, so that's a way of thinking about why compounds like benzene are unreactive with bromine. So a lower electron density means in turn that there's less attraction to an electrophile like bromine. So you need to be able to give that line of argument to explain why there's lower electron density, because you've got 6 electrons spread out around 6 sides rather than 2 electrons localized along one side, and that the lower electron density means that there'll be less attraction to an electrophile. That word attraction is really important there, because they want you to be viewing this as a sort of physical electrostatic force of attraction. That's the key to the mechanism. So you've got to make sure you use that word when you're explaining this. So less attraction to an electrophile, like bromine, but it applies to other ones as well, and consequently you get this low reactivity. The second line of evidence that supports this delocalized model is based on bond lengths. Now, if you remember our definition of a covalent bond, it's the attraction between a shared pair of electrons and the nuclei of 2 atoms. So you sort of have to have this picture that you've got a positively charged nucleus here and a positively charged nucleus here, and then a pair of electrons localized largely in the middle, and so those electrons are pulling the 2 nuclei inwards, and that's what creates the bond. The stronger that force of attraction will be, the more tightly they're going to get pulled together. So the length of a bond correlates with how strong the attractive force between the shared pair and the nuclei are. Now, if you have a double bond, then of course you have 2 pairs of electrons, both pulling the nuclei inwards, and so overall you're going to get a significantly stronger force of attraction than when you just have a double bond. And the consequence is that double bonds are shorter than single bonds. And these are the measured values. You can measure bond lengths quite accurately these days. This wasn't something you could do back in Kekulé's day. This was far in the future as far as they were concerned, but today, using methods like X-ray crystallography, you can measure these numbers very accurately, and what you find is that C single bond C is typically 1.5 times 10 to the minus 10 meters, and the C double bond C significantly shorter at about 1.3 or so times 10 to the minus 10 meters. So, that being the case, we can predict that if the Kekulé structure was right, the shape of benzene should be a sort of distorted hexagon, because you should have a long single bond and then a short double bond. I'm just exaggerating here to make the point, and then another long single bond, and then another short double bond, and then another long single bond, and then another short double bond. And so you end up with a sort of distorted shape to your hexagon. So the Kekulé structure predicts alternating long and short bonds. But when you actually measure them, you find that they're all the same. So this predicts equal bond length all the way around. So, C to C bond lengths all around the ring, because the electron density is evenly spread out. So this is what you find. That's not what you find when you do the experiment. So this is found by experiment, and so that's very strong evidence in favour of the delocalized model. And the bond length, you don't have to memorise these numbers, really just talking about the equality of the C bond lengths is enough. But the bond length, interestingly, is in between there and there. So the bond lengths are about 1.4 times 10 to the minus 10 meters. So it's intermediate between there and there. And that is, qualitatively at least, what you would expect from the delocalized model, because the pi electron density in between any pair of carbons is obviously greater than it would be if you just had a single bond there, but it's not as great as it would be with a localized double bond. So the attractive force pulling each pair of carbons together is intermediate between the two. The third line of evidence that you need to know about is a little bit more complicated to get your head around to start with, and you have to practice describing it, because you do need to be able to describe these data and how they relate to this issue of is benzene delocalized or not. So you know that if we have cyclohexene, like any alkene, you can add hydrogen to it. Okay, so it's just an addition reaction, use a nickel catalyst, and you can turn it into cyclohexane. And you can measure the enthalpy change for that reaction, and you find that it's exothermic, and delta H is about minus 120 kilojoules per mole. So if the Kekulé structure was right, so if it was that, you can see that it's closely related to this. It's just that instead of having so if the Kekulé structure was right, then you can see it's closely related to that, except that instead of just having one pi bond to add hydrogen across, you have three of them. But because they're all constrained in the same kind of geometry, you would expect the enthalpy change for each one of these individual pi bonds to be more or less the same as that one. So we can make a prediction that if this reacts with 3 moles of hydrogen to make the same product, cyclohexane, then delta H should be about minus 120 times 3, which is minus 360 kilojoules per mole predicted. But when you do the experiment, you find that that's not just a bit off, it's massively off. It's actually more like minus 208 kilojoules per mole. So it's much, much less exothermic than you would have predicted. And we have to think about why that is. I think the clearest way to see what's going on with these numbers is to show them on an enthalpy profile diagram. So we have enthalpy rising up there, and we've seen, starting with cyclohexene, which is here, plus hydrogen, that going from there to cyclohexane is exothermic, so that means cyclohexane is on a lower enthalpy level, so that you have an exothermic reaction there to give you cyclohexane, and that's minus 120. What we've also said is that if you use that together with the Kekulé structure to make a prediction for benzene, you would say, well, benzene's just like that, but 3 times, 3 pi bonds. So we would predict minus 360. Since you're still ending up with the same compound, obviously the enthalpy level of cyclohexane is what it is. So if delta H is minus 360, that means you must be starting from a much higher level up here. So this would be benzene as shown by the Kekulé structure, plus 3 hydrogens going down there, and that's minus 360. But remember, that's not a real number, that's what would be predicted based on this simple model. And then we do the experiment and we find out it just doesn't work, because the actual number is nothing like that, and it's not as low as that, but it's somewhere in between. It's somewhere sort of around here. So this is real benzene, and we're going to just get slightly ahead of ourselves and draw it like this. And say, right, this is the actual experimental value, is about minus 208 kilojoules per mole, and that's the actual delta H. So by drawing them on a diagram like this, you can see that what these numbers mean is that benzene has a much lower energy than you would expect based on the Kekulé model. That must be the case, that this has a lower energy than that structure would suggest you would have, because we're all ending up at the same level, so that there's no question of this level being different. It must be these ones at the top. And you can sort of look at the difference between there and here, and people sometimes call it the delocalization energy. In other words, it's the amount in energy terms by which benzene is more stable as a result of what's wrong with the Kekulé model, and what we're suggesting is what's wrong with it is that it ignores delocalization. So you factor the delocalization in, it lowers the energy by that much, and you can see it's a lot. So this evidence doesn't directly tell you there's delocalization. What it does tell you is that the Kekulé structure doesn't look right, that there must be something else going on. And when you combine that with the other bits of evidence, it says, yeah, it would fit with delocalization, and delocalization makes a big difference. It makes the energy much lower than you would expect. Now, you don't have to be able to explain why that is. That's actually a very interesting thing. It has to do with the sort of wave function theory of electrons and the curvature of the wave function and complicated things that are way beyond A level. So we're not getting into that at the moment, but it is important that delocalization leads to lower energy states than you get when you have localized electrons. Although benzene has this low reactivity with electrophiles compared to what one would expect based on the Kekulé structure, it's not completely unreactive. We've already seen it react with hydrogen, but that's not an electrophilic reaction, that's a radical reaction. But it will do reactions with electrophiles if they're really reactive, or more commonly, if you put a catalyst in there, and that's something we'll learn much more about later. But you can get benzene to react with bromine if you put a suitable catalyst in there. So it will react in the dark only in the presence of a catalyst, so it doesn't undermine what we've already said about its low reactivity, but you can get it to react. And of course, what you would expect, based on what alkenes do, is to get addition. Okay, so the expected reaction would be that you would add bromine across there, and across there, and across there. So if it just reacted once, you would get this, or if it reacted 3 times, if you had excess bromine, then you'd get bromine all the way across there, and you would end up with a saturated compound. Okay, so 1, 2, 3, 4, 5, 6 hexabromocyclohexane is what you would predict. But that's not what happens. So what you find is that you get a completely different reaction. In the presence of a catalyst, what happens is you get a substitution reaction. So afterwards, it's still got its intact pi bonds, and all that's happened is that one of the hydrogens has been replaced by a bromine, and you get HBr. So it looks like a radical substitution equation, but it's not a radical reaction. That's an electrophilic reaction, and we'll look at its mechanism in detail later. But the important thing is that reaction with electrophiles leads to substitution rather than addition, which is what would be expected by analogy with alkenes. Now that again fits in with the evidence from the reaction with hydrogen, which told us that delocalization of the pi electrons lowers their energy, makes them more stable than you would expect them to be based on this model. So what we're saying is that really benzene looks like this, and that the reason you get this reaction happening rather than the addition is because if it's favourable to have a delocalised pi system, then it's favourable to keep it. And of course addition would have destroyed it, but by having a substitution reaction you keep the delocalised system intact. So this again supports the idea that delocalisation takes the pi electrons into a more stable state, in this case with the outcome that reactions tend to try to keep that delocalisation intact.